Hello and welcome to Chapter 10 on acids, bases, and salts. Hopefully the volume will work better on this one. These are the topics that we'll be covering throughout this lecture, and we do get to skip these three sections of this course, or this chapter right here. A Nobel Prize winner in chemistry, Cervantes Arrhenius was the first person to classify acids and bases. And according to Cervantes Arrhenius' definition of an acid, this is something that furnishes hydrogen ions when it's going into solution. So if we take a look at this compound right here, it technically should have an AQ after, meaning that it's dissolved in water. Everything should technically have an AQ after it. And when this breaks down into water, it furnishes hydrogen ions. And that was his definition of an acid. And the same thing goes along with base. He said that a base is something that has hydroxide ions. And when we look at sodium hydroxide, it's going to break down into sodium ions and hydroxide ions. This is why his definition has been modified throughout the years, because there are other bases besides hydroxides. Ammonia is a very strong base, but according to Arrhenius' definition, it's not a base. So these definitions will be changed. Here are some properties of acids. They do taste sour. If you've ever had citric acid and lemonade, you know that this is sour. Don't try this at home with any household items, please. They do conduct electricity. Some are very strong electrolytes, some are very weak electrolytes. They react with metals to form hydrogen gas. This is why sometimes it's dangerous to use chemicals in your sinks, especially if you have metal pipes at home. They do change indicators from blue to red, and they react with bases to form a water and a salt. Naming acids is a pretty important skill that the book seems to skip over for the moment, so we're going to get right into naming acids and bases and coming up with the formulas. So again, an acid is something that starts with an H, and usually it's dissolved in water, so you will see that AQ afterwards. So the general formula is H plus some negative ion, whether it's from the periodic table or whether it's from the polyatomic ions. Either way, it starts with an H. So here is something that is a gas. We name it as an ionic compound, so hydrogen chloride. Here is something that's an acid. We name it as an acid. Okay, so there are some rules that we're going to follow in order to name acids, and there will be rules that we follow for naming bases as well. So the name is going to focus on the negative ion that's present. So when the negative ion ends in IDE, typically it comes off the periodic table. You're going to add the prefix hydro on the front. You're going to keep the stem of the negative ion, and then you're going to add ic to the end. Something like HCl. This is the chloride ion. Notice it ends in IDE, so we have to put hydro on the front, keep the stem, chlor, and then add ic, and then add the word acid on the end. And that's how you name that particular ion. When our negative ion ends in ITE, typically it comes off our list of polyatomic ions, or if it ends in OUS, or it's going to change to OUS, I'm sorry, then something like HNO2, that is the nitrite ion, and ite changes to us, and then you put acid on the end, so you have nitrous acid. If your negative ion ends in ATE, nope. Notice on these two rules here, there's no hydro on either one, but we're going to change the ate to ic, and then add the word acid on the end. Something like H3PO4. This is the phos phosphate ion. 8 changes to ick, and you add the word acid. This one has a weird spelling addition. You're going to have to add the OR back in there. So this is phosphoric acid. Notice no prefix on the front. Here's a few for you to try. HBr, H2SO4, and H3PO3. I encourage you to take a second and pause the video, sorry about that extra squiggly line there, and see if you could name these acids using the rules that we just covered. So welcome back. That is the bromide ion, ends in IDE. We need that prefix on the front, so that's hydro, brom, and then add ic on the end. Notice those two additions, our stem is the same, and then put acid on the end. This one is another weird spelling, but it is the sulfate ion. 8 changes to ic, and then add acid on the end, but this one you have to add the UR back in there, sulfuric acid, that's battery acid. And this one is the phosphite ion. Ite changes to us, but this one is a weird spelling as well. You got to add the OR back in there. So this is phosphorus acid. Ionization is just the fancy term that is used to denote that we're going to form positive and negative ions in solution. And that's what Arrhenius' definition is, saying that acids will furnish H plus ions and a negative ion in solution. Dissociation is almost the exact same process, but we're really talking about ionic compounds. These are more like bases, something like NaOH. When it's put into water, okay, it's going to furnish Na plus ions and OH minus ions. The fact that it's given off OH minus ion, that's just dissociation. Here's just a picture showing you what's happening that I've been trying to do. Okay, here is an acid right here. Okay, notice the H and some negative ion. That's an A for anion. When it goes into solution, it's going to produce these hydrogen ions and your negative ion. Here's a metal and our hydroxide ion. Okay, notice when it goes into solution, it dissociates, and we form the positive ion and the negative hydroxide ion. Here's a sample question for you to take a second and read and see if you can figure out the answer. I encourage you to pause the video, read each question carefully, and see if you can calculate, or not calculate, but come up with the right answer. Hopefully you paused the video and came up with C for your correct answer on this multiple choice question. Here are some properties of bases. They also react with acids to form water and a salt. They taste bitter. Again, don't try this at home. They feel slippery. This is why soaps are bases. They can also conduct electricity. Some do it very well, some don't do it very well at all. And they change our indicator paper from red to blue. So remember all those B's. Bases, bitter and blue. Naming of bases is the same as any other ionic compound. So you just name it as you would any other ionic compound. Name the cation, and then the name of the anion. Careful with the transition elements. Okay, and always, of course, crisscross your charges when you need to figure out the formula for those particular bases. So if we were going to do something like calcium hydroxide and come up with the formula for it. Got to remember calcium is a 2 plus ion, hydroxide is a minus. Take those charges and crisscross them. You would end up with CaOH2. Make sure you put polyatomic ions in parentheses. Here's a learning check for you. I encourage you to pause the video and try to figure out the answers yourself and see if you are correct. Welcome back. What ion is responsible for the properties of acids and bases? And you got to remember that this is your H plus ion and this is your OH minus ion. This down here wants you to describe the term that's used for the formation, whether it is ionization or dissociation. Okay, hopefully I put those in the right order for you and you got those. I'm not going to write them out. Here is another learning check for you. I encourage you to pause the video and see if you can get the correct answers before I write them out. But we're going to classify each of the following properties as either an acid or a base. Remember, this is an acid, this is a base. Remember those B's. Okay. Going to do the same thing for the next one. Changes our litmus paper to red. That's an acid. And remember, our bases turn litmus paper to blue. This wants you to write an equation depicting the behavior. So again, I encourage you to pause the video and see if you can get the right answer. So when this goes into solution, it's going to furnish H plus ions in solution and I minus ions in solution. This will be the same thing, but in this case, we have the chloride, the chlorite ion, and that's going to give us H plus ions in solution plus the ClO minus ions in solution. This is a base, and again, it's going to furnish our lithium ions in solution and our hydroxide ions in solution. And this one will do the same thing. Hope that you got those right answers. Here's a more inclusive concept of the acid-base theory, and this is developed by two gentlemen, Bronsted and Lowry, and they claim that a substance, if it donates a hydrogen ion, then it's said to be an acid. If it's a base, then it's going to accept the hydrogen ion. So it's all about following the hydrogen ion or the proton, or sometimes it's denoted as H3O plus for this acid. So this one, you kind of got to get used to having three different terms for an acid. Here is a multiple choice question for describing Bronsted-Lowry acid bases. Pause the video, see if you can get the right answer. Here is the correct answer. Pause the video and read it in case you didn't get it. Here's just an equation showing you that something is in equilibrium here, and we got to try to identify what is an acid, what is a base, so we follow the H. Okay, this one lost an H, so by definition this one is the acid. It donated an H. If you look at this one afterwards, this one accepted the H. So if it accepts an H, then it's a base. And you got to go the same thing going back. Okay, this one on the way back didn't have an H to donate, so it must be what's known as our conjugate base. And this one lost an H on the way back. It started with 3 H's and ended up with 2. That is what's known as our conjugate acid. So you got to be able to go both ways across that equilibrium sign. Here is another multiple choice question. I encourage you to pause the video, read it, think about it, and see if you come up with the correct answer. Here is the correct answer. I hope that you got it. If not, go back, review, and see if you can figure out what you did wrong. Sometimes Sometimes there are species that can act either as an acid or a base. They're known as amphiprotic substances, and here are a few examples listed underneath: water, hydronium, hydroxide. Water's on there twice. Here is some more practice, and I encourage you to pause the video, see if you can figure out whether the first reactant is an acid or a base. So we look at the first one. This one has an H, and we look at it afterwards, it lost an H, so that one must be an acid. The first one doesn't even have an H to donate, but if we look at it afterwards, he accepted the H, that is a base. Here we have an H to donate, and if we look at this species afterwards, it did donate an H, so that's an acid. And then our first species, okay, look at it afterwards, it accepted another H, so that's a base. Here's some more practice for us. I encourage you to pause the video, go back and look at the definition of a conjugate acid and conjugate base. Remember, there are species that vary by one hydrogen ion. So for the first one, this one is going to lose an H, and your species on the other side of the equation will be HSO3 with a minus charge. This one, we are looking for a variation by one H, and the conjugate acid will be looking like this because it needs to lose that H right there. The next one will vary by one H again, and it will be C2O4 with a 2 minus charge. And the final one, again varying by one H, and the conjugate acid of this one will vary by one H, and it has one extra, and it's PO4 with a minus charge. Another learning check, I encourage you to pause the video and try to identify the conjugate acid base pairs. We're just going to identify everything. Looking at the first one, this one has an H, on the other side it doesn't, so this is our acid, this is our conjugate base. This by default, acids and bases always come in pairs, so this is our base, this must be our conjugate acid. Doing the same exact thing on the next one, we look at this species and then look at over here, it's lost an H, so this is our acid, this is our conjugate base. This one must be our base, and this one must be our conjugate acid. Those are not conjugate visits or conjugal visits. Haha. In this next section, we're just going to look at mono, di, and triproduct acids. Mono meaning one. This one only has one hydrogen ion to supply during an acid-base reaction. Diproduct means it has two. Okay, and this one has two protons or hydrogen ions that it can donate during a acid-base reaction. And triproduct means it has three protons that it can donate in an acid-base reaction. Poly meaning many. This has more than one hydrogen ion that it can donate, so 2 to 3. So diproduct and triproduct acids fit in polyproduct category. Here is a learning check. I encourage you to pause the video, read the question carefully, look through all the choices, come up with a correct answer, and hopefully you get the right one. Here is the correct answer. I hope that you got it. If not, go back and review what mono, di, and triproduct acids are. Here's another learning check for us. We're going to try to figure out whether they're mono, di, or triproduct acids, so I encourage you to pause the video, see if you can get them before I put the answers up there. There's only one H there, so that's the monoproduct. One H here, even though there's some right there that doesn't count. This again is monoproduct. This one has three H's out in the front. These ones don't matter. This is triproduct. Here's another one that's soda, pretty much phosphoric acid. That's triproduct, and our last one down here, sulfuric acid, that is a diproduct. Strong acids will transfer almost 100% of its protons to water in this reaction right here. So you will end up getting H3O plus and Cl minus. The equilibrium lies heavily to to the right in this case, with a very small percentage going to the left, and that's just saying that's a strong acid. Weak acids, this will be flipped around. It will be very small going to the right and a lot going to the left. Here is a list of the most commonly strong encountered acids. I would make a copy of this for your homework. This I guarantee will come up. This is what I was talking about 2 slides ago, with our equilibrium lying heavily to the left and very little going to the right. This weak acid would be something like acetic acid that we can put on our salads and eat as vinegar. Here's just a pictorial representation showing a strong acid having that proton right there, but afterwards the proton has been transferred to water and we end up with our negative ion. Most of our stuff will go this way. However, when we have a weak acid, it's going to favor this reaction right here. Most of the stuff will be left as the acid. There will be a little bit of our acid and negative ion showing. Here's a list of strong bases. This is going to be the same kind of reaction where most of our stuff will dissociate and we'll end up with Li plus OH minus ions. The fact that it dissociates tells us that it's a strong base, and here are a list of common strong bases. That'd be very, very helpful for homework, so I'd copy that list down. Here's a practice multiple choice question. I encourage you to pause the video, look through the answers, and see if you can guess which one would depict a strong acid. And hopefully you picked B for this one. As always, I encourage you to pause the video, see if you can figure out whether the first member of the pair is stronger or weaker. Hopefully you came back and found that this one is stronger, this one is stronger, so this one is weaker. This one is weaker, and this one is also weaker. So this is a stronger one right here. Here's another learning check for us. Again, I encourage you to look at the problem, go back at those lists and see if you can determine whether the acid and base indicated are both classified as strong. And all 3 of these would have been classified as strong for each one, but this one is weak right here. So that one would not have been a good category or a good fit. As always, I always encourage you to pause the video, read the problem, see if you can come up with the answers before I go through them. So hopefully welcome back. And for question 1037, there's 4 diagrams of acids, 1, 2, 3, and 4, that represent different acids. We are looking for the one that has the strongest acid for 1037. And for that one, we would be looking for the one that is broken up the most, or is the most ionized, so that would be diagram 4 for 37. In 38, we are looking for the weakest acid, so we are looking for the one that breaks up the least, and that would be diagram 3. That one breaks up the least, so this is for 38. For 1039, we are looking for terms like weak, strong, mono, di, or triproduct. And both of these have 3 out there on their H's, so they're both triproduct, and they're both weak acids. Again, go back and look at the list of strong acids and strong bases for the answers. Here is a very useful formula for calculating the acid ionization constant. This is an equilibrium expression, so remember we're going to put our products over our reactants, and we only do aqueous for acids. So that's why this is going to go here, and this here, and this is going to go on the bottom. Here are a couple good rules of thumb for determining whether an acid is going to be strong or not. The acid strength is going to increase with the percent that's ionizing. That means the more it dissociates, or the more our arrow favors this way versus this way, the stronger it's going to be. The strength of our acid is also going to increase with an increase in our Ka magnitude, the formula that we just looked at on the previous slide. and a percent ionization increases with an increase in magnitude of Ka as well. We have a very similar equation for bases. This is the base ionization constant. Okay, that's going to be known as Kb. And remember, it's our reactants over our products. Okay, and this will go up here, and this will go down here, and the water doesn't play a factor. Again, here is a learning check. I encourage you to pause the video, see if you can come up with the answers, and come back. For the first one, I gave you the answer where you could see it, and that's your ionization constant. Expression for acetic acid, you're going to do Ka is going to be equal to, and again, hopefully you're doing this on your own, but it's your hydrogen ion concentration times your acetate ion concentration, which this can be written in several different ways. This one is one of the more common. That's minus all over your original acid, which is listed right over there on the side, HC2H3O2. These constants for 10-42 are going to be very, very similar. So I'll write them here and try to squeeze them in. This is a cyanide ion all over your acid concentration. And doing the same thing for the next one. You're going to have Ka is equal to your H plus concentration. Sorry for the sloppiness there, and over your original acid. Here is another learning check for us, and we're trying to use this table over here to indicate which acid is stronger out of the two. And for 10-45, looking at this one versus this one, you're looking here versus here, and this is higher for Ka and the percent ionization character, so you're going to be circling this one. For B, you're going to do the same thing. I encourage you to pause the video, see if you can find everything on our list, and you'll find that HF is going to be stronger. For the next one, this one is going to be stronger, and for the last one, this one is going to be stronger. Use the chart. That's very, very helpful. Book is going to talk a little bit about salts, because a lot of times when you mix an acid and a base, you get a water and a salt. So it's worth reviewing what an ionic compound is. Usually it's a metal and some negative ion, whether it's from the periodic table or whether it's from our list of polyatomic ions. That's what a salt is. There's solubility rules that you should review that help us decide whether something is going to dissociate or fall into ions in solution. Here is a sample multiple choice where we're trying to figure out how does a chemist define a salt. So I encourage you to pause the video, see if you can come up with the answer. Hopefully that's the answer that you got. Another learning check, we're trying to figure out if something is an acid, a base, or a salt. So I hope that you're coming back after you've taken a stab at some of these. Generally anything that starts with an H, that's going to be an acid. This is a positive and a negative ion, so that's going to be a salt. This is ammonium nitrate, that's also a positive negative ion, so another salt here. And typically anything that ends in OH is typically going to be a base. Think of Arrhenius's definitions of acids, bases. That will very much help you with deciding whether something is an acid or a base. In this sample problem, we're trying to figure out whether both members of each of the following pairs are salts. And with this one, they are in fact both salts. This one is potassium cyanide and this one is sodium cyanide. This one here is an acid, so that one doesn't fit. Here, this one over here is a base, that one doesn't fit. But the last one, those are both salt. Aluminum nitrate and calcium nitrate are both salts. Here is an example of a neutralization reaction where we're going to have an acid
mixed with a base, and our products are a salt and a water. And you can see that's going to happen with hydrochloric acid and potassium hydroxide to form water and a salt here. Another one is written right underneath it with sulfuric acid and potassium hydroxide, where we're getting potassium sulfate and water. Notice they wrote water properly, where this is just showing that water can be part acid and part base. Here is a sample multiple choice where we're looking at a neutralization reaction and we're trying to figure out what the products are. Hopefully you take a stab at it and came up with this answer right here. Here's a learning check to find out if you can figure out which of the following reactions are acid-base neutralization reactions. And when we look here, this is not. This is a reaction between a couple salts, so this is no good. Here is nitric acid and sodium hydroxide making a water and a salt, so that's a good one. Next one, that's an acid, that's a base. We end up with a water and a salt. That's a good one there too. We do have an acid here, but this is not a base, it's a salt, so that one doesn't fit our criteria. I did mention a few slides ago that water is part acid and part base, and it does self-ionize to a very small extent, and we can see that here with water forming part acid and part base. The net effect of the formation is equal amounts of the hydronium ion, this is hydronium, and the hydroxide ion. Equal amounts, that'll be very important. At about room temperature, we end up with this equation right here. This is known as the ion product constant for water. Sometimes I like to make little circle charts out of this. I'm not sure if you've seen these little circle charts, but whatever it is that you're going to be looking for, you cover it up. So if you're looking for the hydroxide, you would cover this up or shade it in, and you just take essentially this 1 times 10 to the minus 14. I like to use E in my calculator, and in order to get the E, you hit the second function button in your calculator, and then it's usually a comma on a graphing calculator, but it says EE in the background. Rather than writing this right here, I'd like you to use that E to get less order of operation mistakes. So anyways, type this number in your calculator and then divide by whatever concentration they give you to determine what the other one is. Here's a graph showing us that right at 10 to the minus 7 for each, we have equal concentrations of acid and base. But as our acid character goes up, our pH or our OH minus concentration goes down, and vice versa is being shown right here. The graphic on the last slide showed us that when our concentrations are equal, we have neutral. As our acid concentration starts to go up, our OH minus concentration will start to go down. We end up in the acidic range, and again, vice versa. When our hydroxide tends to go up, our hydronium will tend to go down, and we have a basic solution. So this is the circle equation that I was just talking about. In this particular question, we're trying to figure out what is the molar hydronium ion concentration in aqueous solution with the following hydroxide. So this is our OH minus concentration. And we're going to take that 1e to the minus 14, and that's molarity squared, divided by 3.5 e to the minus 3, and that's just m. Then you get one of these molarity square or canceling, and when you do that in your calculator, you should end up with 2.9 e to the minus 12. We're going to do essentially the same thing for all of these. Divided by 4.7 e to the minus 6. M, again, your m's will cancel. Doing this one, you're going to end up with 2.1 e to the minus 9. Now when you're putting this in your homework, you're going to want to do 2.1 times 10 to the minus 9. Okay, but I tried to show you what the calculator is going to spit out at you. Doing the same exact process for C, you're going to end up with 9.1 e to the minus 7. And for D, you're going to end up with 1.1 e to the minus 5, and those are both molarities. Again, here you're doing essentially the same thing, 1 e to the minus 14 divided by the concentration that they give you. That's going to turn out to be 3.03 e to the minus 12, and that is going to be basic. Doing the same thing over here, you're going to end up with 1.47 e to the minus 7, and this is just slightly basic. Here's another exercise essentially doing the same thing. I'm going to put the answers up here. I hope that you are pausing the video and trying to figure these out for yourselves. There is your answers. I hope that you were successful. Here is a multiple choice question. As always, please pause the video, read through the choices carefully, see if you can figure it out before it just pops up there. Hopefully you selected C for your answer. You may have been asking yourself, how did I come up with whether it's an acid or a base? The easiest way I think to do that is to use this equation right here, where the pH, or the power of the hydrogen, is equal to the negative log of your hydronium or your H plus concentration, whatever they give you, however it's stated. They're used interchangeably a lot. So it's a compact way to take a huge range of numbers and pack it into a small scale that goes between 0 and 14, with 7 being neutral, less than 7 is acidic, and greater than 7 is basic. So here is a sample problem where you might have to use your pH scale. I'll put it up here. And in order to figure out the pH here, you're just going to plug in this number right in there. Now you got to be careful here. You might have to use the equation that we just used and figure out your H3O plus concentration by dividing this by 1 e to the minus 14 and then plugging your new value in there, and hopefully when you do that you're going to end up with these answers right here. From here it's pretty easy to say that this one is an acid and the bottom one is a base. On this particular problem you got to go the opposite way. So what I do on my calculator is I hit second function and then hit the log button, and that should bring up 10 carat, and then you're going to do a negative pH. So 10 carat negative pH, or 10 raised to the negative 5.85, and that should give you this answer. That's your answer. Here's some more practice for us to try. So in this one, all you got to do is take the negative log of your H3O plus concentration, and they give us that. That's going to be plugged in right there, and you're just going to end up with 5 for the first one. Doing the same thing, but plugging the value of that value in, you'll end up with 8 for the next one. Now you got to be careful on the next one because they give us the hydroxide ion concentration, and for that one you have to use this equation right here first. That should be 1 e to the minus 14. I know I got a little sloppy over there, so you're going to have to divide this by, or take 1 e to the minus 14 and divide this number. That's going to get you a value of 1.00 e to the minus 10, and that's going to give you a pH of 10, because you can take the negative log of this value right here, and that will give you 10. You're going to do the same exact thing, so 1 e to the minus 14 divided by this, that would give you 1 e to the minus 4, and that's going to be equal to 4. This is using the pH formula. Oh, that's a laser pointer, sorry. Where I have to use the pH is equal to the negative log of your H3O plus concentration. So in this one, you're going to have to do the anti-log, which in your calculator will come up as 10 caret, and then you do negative pH. And when you do this one, this should be 1.00 e to the negative 4. This one, 1.00 e to the negative 6 when you do that one. And when you do the last one, I got to do this one real quick. I end up with 4.57 e to the negative 5. And again, when you're putting these in your homework, use times 10 raised to the negative 6. You don't need a double negative. I had mentioned this before, but pH of 7 is neutral. pH greater than 7 is basic, and pH less than 7 is acidic. Here's a multiple choice question. I encourage you to pause the video, read the question, see if you can come up with the correct answer, and hopefully when you did, you selected A for your answer. A little bit more practice for us. When we have a pH of 6.4 and we're trying to determine these three categories, that definitely falls in the acid range. This falls in the basic range. This is pretty close to neutral, but it is slightly basic, and this one is acidic. In addition to having the pH scale to judge acid strength, we can also use pKa values, and that's just the negative log of your Ka value. pKa is calculated from the Ka in exactly the same way that you would calculate the pH of a solution. Here is an example of that very same thing that we just talked about. And we're going to try to calculate the pKa for hydrofluoric acid given the Ka for this acid is here. So pKa is equal to the negative log of your Ka value. So you got to do the negative log. Negative 4. And when you do that, you should end up with 3.17 roughly. Here is more of the same. Again, you're going to use pKa is equal to the negative log of your Ka value. This one is done for us. The next one, when you run it through your calculator, should give you 6.37 roughly. Next one should give you about 7.21, and the last one should give you about 1.8 for your answer. These were only given in two significant figures, so I should probably only have two significant figures in my answers, but they chose 3. Here's a multiple choice question for us. I encourage you to pause the video, see if you can come up with the correct answer, and run with it. Here is your answer. Hopefully you got the right one. Section 10.11 is about salts. Remember, salts are ionic compounds. They're made up of positive and negative ions. When they are put in water, they do break up or dissociate into their individual ions, and the hydrolysis is defined as the reaction of a salt with water to produce any one of these three things: a hydronium ion, hydroxide ions, or both hydronium, that's a hydronium, and hydroxide ions are right here. And it could produce both. Types of salt hydrolysis, you got to pay attention to the strength of the acid and the strength of the base. So when we have a strong acid and a strong base that does not hydrolyze, so the solution is neutral, you could end up with something like sodium chloride or potassium bromide. When we have a strong acid and a weak base, it can hydrolyze to produce acidic solution, something like ammonium chloride. Third type of interaction, we could have a weak acid and a strong base to hydrolyze to produce a basic solution. something like sodium acetate. Or our last type, we could have a weak acid and a weak base hydrolyzed to produce a slightly acidic, neutral, or slightly basic solution, depending on the relative weakness of the acid and the base. Here is a table showing you everything that I just mentioned. Hopefully, when you see a strong acid and a weak base, it would make sense that the nature of it would be acidic, or vice versa. Here is a sample question. Again, I encourage you to pause the video, see if you can read it, come up with the correct answer. After reading it and looking through your choices, hopefully you picked this one to be your correct answer. 10.11 is about buffers, and a buffer is an aqueous solution containing substances that prevent major changes in pH when small amounts of acid or bases are added to it. A good example would be your blood has a typical buffer in it, and if something happens like you hyperventilate, that buffer will help prevent your blood from going too acidic or too basic, depending on whether you're getting too much carbon dioxide or not enough carbon dioxide. But we want that because if you go into acidosis, you could die. So a buffer is made up of a weak acid and its conjugate base. So therefore, it has two active species in it. If a substance is added, we can remove a base or remove the acid from that buffer to maintain our pH range. So we have substances to both react with the acid and the base if it's added to the system. This is telling us what happens if we add a base to our system with a buffer in it. The added OH ions react with the hydronium ion, producing water, which is a neutralization reaction. This neutralization reaction produces the stress, but not enough of the H3O plus ions cause it to change its pH. So the equilibrium will shift to the right to produce more hydronium ions, which will maintain a pH close to the original level. A very similar process will be done if acid is added to the solution. So if we have too much H3O plus ions, then our equilibrium will shift to the left, consuming most of the H3O plus ions and resulting in a pH level that's close to the original. Here's a multiple choice question about buffers. Take a second and read these carefully. There's some good choices there. Hopefully this is the one that you selected about this particular question. Here we're going to write some equations for what's happening to our buffer. So we have this system right here, and we're going to add the H3O plus. Notice we've added it to this side, and we end up getting these products right here. For the next one, it's going to be the H2, the carbonic acid, and the addition of the hydroxide ions to give us HC3O minus plus H2O. Next one, now you gotta be careful, we're adding acid to this one, so the acid reacts with the conjugate base. And I started to write that one wrong. It should be CO3 with a 2 minus plus the H3O plus is going to give us this and our water. And the last one, we're going to add our base to it, so we want our our phosphoric acid reacting with the OH minus that we're adding, and we're going to end up getting H2PO4 with a minus plus our water. Looking at the slideshow, we just skipped a couple sections. We don't have to cover those sections in our course, but the last section that we have to cover is acid-base titration. This is really a neutralization reaction in which a small measured amount of acid or base of an unknown concentration is completely reacted with a known volume of and a known concentration of a base or an acid to figure out our concentration of our unknown. Kind of a fun little lab. If we were in, well, if when we do it, if we did it, it would be one where you have a big burette and you titrate slowly into your acid or base until you see a change in color with the indicator that has been selected. Usually it's phenolphthalein and it changes to a pink color. Here is a setup with what the burette would look like right here, and you would slowly titrate your known concentration and your known volume of either the acid or a base into this Erlenmeyer flask down at the bottom and wait for the drop that keeps it pink. With the information that you have, then you can calculate what your unknown strength is. As I mentioned, there are different indicators that could be used. These are compounds that exhibit different colors in solutions depending on the pH of that. So we would be looking for something that changes to a pink or a blue typically. Indicator is selected that changes color at the pH that corresponds as nearly as possible to the pH of the solution when the titration is done. Here you can see titration is being done, and we are looking for, in this case, the pinkish purple color that's produced at the end of this titration experiment. Here is a sample question. Okay, I always think it's helpful to have the balanced acid-base reaction that's going on, so I'm going to put that up here at the top. Sorry about that. And balancing this real quick, you'd have to put a 2 right there and a 2 right there. So now we can start usually the process, and it's usually a 3-step process, but this one is only 2. First is this equation here, then we relate our mole to mole, and then we go back to this equation right here. Whoops. So in this case, for a titration of sulfuric acid with sodium hydroxide, how many moles of NaOH do we need to react with this right here? So that is step number 1. Our molarity is 0.5. That's really moles per liter, is equal to our moles that we're looking for. So we can do to the next step all over 1 liter. And 1 times 0.5 gives us 0.5 moles of H2SO4. Now in this one, they want to know how many moles of sodium hydroxide, so all we got to do is step number 2, 0.5 moles of H2SO4. Set up our relationship between the H2SO4. There's one of those, so 1 mole H2SO4, and then there are 2 moles of NaOH. These would cancel. 0.5 times 2 is going to give us 1 mole of NaOH. One of our last multiple choice practice problems. Again, pause the video, read the question carefully, see if you can find the best answer. The best answer in this case would have been B. A few more multiple choice questions to try. Take the negative log of this, and you can figure out your pH, which that didn't help you, but that will help you figure out whether it's acidic, basic, or neutral. And then do your 1e to the minus 14 divided by the concentration that they give you to come up with this answer here. This looks to be like a titration experiment. Careful with your units. They will cancel out in the end if you leave them in milliliters, so that's okay. But this is where you might have to do your 3 steps. There's your answer. Thanks for tuning in. Have a wonderful day.